Today in physics, we would like to talk about Newton's law of universal gravitation. You see, Newton had spent a lot of time observing the world around him, and he had developed relationships among forces of objects that were in equilibrium and an understanding of what would cause something to change or accelerate, and then this interaction between other objects, and we've come to know these as Newton's first, second, and third laws. But as Newton was taking in his observations about the universe around him, he maybe considered an apple in a tree. And if he saw that apple fall from the tree, he thought, well, perhaps there must be a force on that apple pulling it down. And that force on the apple is probably proportional to the mass of the apple. But then he also knew that if the apple was attracted to the earth, then the earth must also be attracted to the apple, which is what we would come to find in Newton's third law. He figured that the force that the earth pulls on the apple with must also be proportional to the mass of the earth. And then, kind of like what we would find if we play with magnets and we feel the force between two magnets is stronger when they're closer together and weaker when they're further apart, Newton theorized that the same thing was true about the apple and the earth as opposed to the moon and the earth. The farther apart things are, the weaker that force is. And so that force must be proportional to the distance between these two masses. And so he called this attractive force between two things a gravitational force. And he decided that the same laws that hold the apple to the earth must also be the laws that hold the moon to the earth, or the earth and the sun, or our solar system and the galaxy, or all of these bodies in the universe. We call this the law of universal gravitation. According to this formula, F is some constant, which we will call big G, which is a teeny tiny number, but F is big G times the first mass times the second mass divided by the distance between these two things squared. Well, according to this formula, if you take a planet's mass and you double it, then the force between these two things should double. In theory, what we're saying is, if we consider the force to be G times mass 1 times mass 2 divided by, we'll call this the radius, because the distance from Earth to us, from center to center, would be the Earth's radius. But R would be the distance from the center of one object to the center of another. So when we square that, so if you were to put a 2 in front of mass 2, it would simply double the force. Or if you doubled the distance, if we get these things twice as far away from each other, whatever we do to this distance gets squared. And so if you double the distance, now I'm taking this top quantity and dividing by 4, so the force is now 1/4 as much as it was before. This relationship between force and distance is an inverse relationship. And because distance is squared, this is called an inverse squared relationship, or an inverse squared law. We'll come across several of these things in physics. This is the first time that we come across this particular relationship, this inverse squared law. But it's important to remember that whatever we do to the distance gets squared, and that inversely affects the force. Now, big G, that constant that he developed, this is a teeny tiny number. Like our acceleration due to gravity, which we call little g, which we're representing as about 10 meters per second, that's huge compared to big G. Big G is a constant. It has a value of 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. There was a guy named Henry Cavendish that did an experiment to actually come about and measure the value for big G. Because all Newton could get to was that there was this missing constant somewhere, but we knew that these forces were proportional to the mass of each object, and they were inversely proportional to the distance between them squared. We couldn't get the exact number. But the great thing about Cavendish finding this exact value is that other people were able to build on his research, and we were then eventually able to determine the mass of the Earth. Now, think about this. When you stand on a scale, that scale reads your weight. And so you say, well, I wonder how much I weigh, and you step onto the scale, and the scale reads your weight. We can't say, well, I wonder how much the Earth weighs, and just flip the scale over. That doesn't work. So we've had to use math, and this has been done from, like a very long time ago. Aristophanes developed a plan using geometry and the shadow of a sun, or of the sun on a stick, to determine what the circumference of the Earth was. So these things that have been available to us for a long time have become really important to us because we're making some important measurements based on this information. Nobody's directly weighed the Earth, right? But we've used our math relationships appropriately to kind of extrapolate what the weight of the Earth is. So we say that the mass of the Earth is 5.98 times 10 to the 24th kilograms, right? That is super heavy, of course. So what does this affect? Well, if apples can fall to the Earth, and the moon is falling to the Earth, but it's also moving sideways at the same time, we want to kind of think about what does that mean, right? That represents projectile motion. So remember that a projectile is something that has this horizontal velocity and it's free falling toward the Earth. And what we understand about projectiles is that if we consider acceleration due to gravity to be 10 meters per second, then we know that in 1 second an object will fall beneath the position that you've dropped it, a vertical distance of 5 meters approximately, right? And so if something is moving horizontally, it will fall 5 meters beneath that starting position in 1 second. So projectiles that move horizontally and fall because gravity is pulling them down have that curved path. Well, Newton proposed a thought experiment, and he said, well, what if we could take a cannon and put it on a very, very high mountaintop and fire a projectile sideways from that cannon? And we know that the path would be a curve. But as we fired it, what if we could fire it so fast that its velocity and the path, the trajectory that it made, allowed it to match the curve of the Earth's surface. So essentially it would fall around the Earth. And that's how we understand satellites to behave, and the International Space Station and other objects that are in free fall around the Earth. They have a tangential velocity that is fast enough that allows their path that they take to match the curvature of the Earth. And so they essentially fall around the Earth. And that's what gives us these shapes, but it allows us to orbit. In order to do that, certainly we would have to be way high above Earth's atmosphere. We would have to be so high because as an object moves through the atmosphere, those particles are going to create a lot of friction on it. And these objects have to move at like 17,500 miles an hour sideways. That's what our ISS is doing, to be able to orbit in the place that it is orbiting at that height above our Earth. So I'd like to show you an example here of using Newton's law of universal gravitation to just manipulate this equation and figure out what would happen to a person if we could change one of these factors, right? So this is a person weighing 800 newtons on Earth travels to another planet. This other planet has twice the mass and twice the radius of Earth. So the person's weight on this planet would most nearly be what? So remember, using Newton's law of universal gravitation, that force is their weight. So if an M1 will be the mass of the person, M2 will be the mass of the planet. If we double this mass, you can see that that should double the force. But if we were also to put a 2 in front of the radius, Well, this whole thing is going to be divided by 2 squared, which is 4. So now the force is going to be divided by 4. So we would have coefficients in front of this force of multiplying it by 2 but dividing it by 4. Well, this would make 1/2 the current force. So this person's weight would then be 400 newtons. Just manipulating the equation. I didn't have to plug in the actual values, find their mass, find the mass of Earth or this other planet, divide by the distance squared. But it's important to know that I can do those things. Okay, let's take a look at another one. Right, doubling the mass doubles the force. Doubling R reduces the force by 4. So 2 force is 0.5 the force. So half of 800 is 400. Let's take a look at another example here real quick. So this says Mars has a mass 1/10 that of Earth and a diameter half that of Earth. The acceleration of a falling body near the surface of Mars is most nearly what? Well, let's take a look at acceleration, right? We understand acceleration on Earth to be the rate that all things fall. And all things fall that rate because their weight compared to their mass has that very specific ratio. We could say the acceleration due to gravity is equal to the weight, right, divided by the mass. The mass of you divided by your weight. That gives us AG. Well, if we say your weight is now calculated as big G times the mass of you times the mass of the planet divided by the radius of the planet squared, we're putting this value in for FG. Then we need to divide by the mass of you. So you can see I've got mass of you in the top and the bottom. Those are going to go away. And what I'm left with is the acceleration due to gravity anywhere is equal to big G times the mass of the planet divided by the radius of the planet squared. This allows us to find the acceleration due to gravity on Mars, on the moon, on some asteroid. We can essentially find the acceleration due to gravity due to you by taking your mass and your, well, it'd be hard to get your average radius because we'd have to kind of tuck into a tight ball. But we could do that as well as long as we had this big G value, this constant of 6.67 times 10 to the negative 11th. So here, if we have a mass 1/10, if we put 1/10 in front of this, and we know that our AG is 10, 1/10 is going to make this 1/10 as much, right? But then we said they have a diameter half of Earth. Well, if they have a diameter that's half of Earth's diameter, then truly they have a radius that's half of Earth's radius. So we're putting a coefficient right here in front of R of 1/2. But 1/2 squared is 1/4. So what happens to AG? AG, which is 10, right? 10 meters per second squared is our acceleration due to gravity on Earth. This gets a coefficient of 1/10 in the top and 1/4 in the bottom. So I have a fraction over a fraction, and so you know when we do that we have to invert and multiply. So this becomes 1/10 times 4 over 1. So this becomes 4/10 times gravity, 10. So this should be about 4 meters per second instead of 10. Or if we used 9.8, it might be about 6. So it's 4/10. So the acceleration due to gravity on Mars would be about 4 meters per second squared, which I think is about 3.6. Consider that we use 9.8 for Earth's acceleration due to gravity, and this would be about 3.6. So let's do one more thing here. Earlier this year, I asked you to calculate what your mass was. You know, we weigh everything in pounds. And so we said, well, 1 kilogram is 2.2 pounds. So if I take my weight in pounds and divide by 2.2, I can get my mass. Let's say that a person had a mass of 50 kilograms, and we wanted to find their weight. Previously, using an application of Newton's second law that says F equals m times a, we said the force due to gravity is mass times acceleration due to gravity. So we would say that we could calculate the weight of that person by taking their mass times gravity. Now I'm going to use 9.8 because I want to get a little closer here. So if I do 50 kilograms times 9.8 meters per second squared, I get 490 newtons for my 50 kilogram person. This would be their weight on Earth. But we can also use Newton's law of universal gravitation to find the same thing, because this is an attractive force between that person and the Earth. And by the way, that person is not touching the Earth. They're very far away from the Earth. They're currently at 1 Earth radii from the Earth. So if we treat the Earth as a sphere, and we say, okay, let's do the same thing using Newton's law of gravitation, we need to know big G, the constant. We need to know the mass of the person and the mass of Earth, and the radius between, the distance between the two of these two people. So we would say big G is 6.67 times 10 to the negative 11th. Multiply that by the mass of the person. Multiply that by the mass of Earth, 5.98 times 10 to the 24th kilograms. And then the radius of the Earth is about 6.38 times 10 to the 6 meters. But we have to square that distance. And so if we do all of this work with these, making the calculator do what we want it to do, using our parentheses wisely on our exponents, we come up with a force of gravity of 489.95 newtons. How about that? We can find our weight this way, and we can find our weight this way using Newton's law of universal gravitation.